Hello, my name is Javier Rodriguez and welcome to lab number 3 of Physics 2211, Black Hole Orbit Lab. For this lab, we have to identify the mass of a black hole from which a star is orbiting around. Python is utilized to create code that takes in the position data of a star and uses this to calculate the net force, the parallel component of the net force, and the perpendicular component of the net force at various points. The different net forces are then represented using different colored arrows. The arrows will be colored yellow, blue, and perpendicular, and black. The F-net at each point could then be utilized to approximate the mass of the black hole by utilizing Newton's universal law of gravitation. Now, there are a few things that are known before starting our lab. The net force is due to a single force, the gravitation pull of the star from the black hole, located at a location provided in Web assigned. The formula for gravitational force is also known from Newton's gravitational law. In order to use this law, however, we need to find the mass of the black hole, the net force, and r, distance. Both the mass of the star and big G are known in this specific case. The mass of the black hole in the end was found to be 1.99 times 10 to the 31. We're also provided a PHYS spreadsheet that includes the position of the star until it reaches the end of its circulatory path around the black hole. We also know that in order to calculate dp/dt, we can just find the net force, since these two quantities are actually equal. Now, if we go to our code, we begin the code by defining our star and our black hole. We also define our three arrows, the yellow, which will represent the net force, the blue, which will represent the perpendicular component, and the black one, which will represent the parallel component of the force. We also have the mass of the star, big G, and the position of our black hole, which are all provided. Now, if we go to our first loop, we'll see the first important component of our code, which is finding the velocity of our star. In order to do this, we can use x and y, which are the two columns of our CVS file, and utilize this to find velocity. Since velocity is equal to delta r over delta t, we can just take two different positions and divide them by delta t in order to find a velocity. If we do this continuously, we'll find the average velocity of the star. As you can see here, we have the initial and the final velocity of the star. These two quantities can then be utilized to calculate momentum, since momentum is just the mass of the star times the velocity, in this case, the initial velocity and the final velocity. Then, since we know that delta p is equal to F net times delta t, which is equal to delta p times delta t, we can say that F net is actually equal to dp dt, as you can see right here in our code. Now that we have dp dt, we can actually concentrate on finding the two components of dp dt. First up, the parallel component. In order to find this, we can just use the magnitude of our final momentum minus the magnitude of our initial momentum divided by the delta t. This must then be multiplied by p hat, since we know that the parallel component of the force will always aim in the same or opposite direction to the momentum. Now, our dp dt perpendicular has its own formula, but in this case, since we do not have a radius provided of the kissing circle, we can just subtract dp dt parallel from dp dt. Finally, after finding r by subtracting the black hole position from the star position, we can find our black hole mass using Newton's gravitational law. Now, once our code is run, you can see that here's the star moving around, and the parallel component of the force is actually in the same direction as the movement of the star, meaning that the star is actually speeding up. However, towards the end, the black arrow is pointing in the opposite direction, meaning that the ball actually slowed down. Our perpendicular component is, as I mentioned, pointing towards the mid-center of the invisible kissing circle, and the net force, the yellow arrow, is simply pointing towards the black hole. Now, if we go here up to a what does it mean question, we know that the F net is equal to dp dt, and the F net parallel is equal to dp dt parallel, and F net perpendicular is equal to dp dt perpendicular. We know all of this because of the definition of impulse, which is dp dt is equal to F net times delta t. which can be rewritten as delta P over delta T or delta T or dP over dt. This in the end means that Fnet is equal to dP dt, and all the components of Fnet are equal to all the components of dP dt. Finally, a what-if question. Now, if a different black hole were to take the place of a current black hole, and the position data of the star was the same, and so was the position of the black hole, the difference would not be able to be measured in this case. The mass of the black hole will be exactly the same if it continues to be the only force acting on the star, is in the same position as the original black hole, and the star moves in the same path, since these are the only things provided and they are not changed. Thank you for your time.